Okay, so I guess I'll be starting now. So today's lecture is on number theory, as you can see from the title. So first of all, I'm going to be introducing some notation. And so this is the notation. So first off are the integers. So the integers. So the integers are basically the numbers that we normally use, like 1, 0, -1, 5, 3, 10, -2000, 2021, and so on. Yes. So those are the standard integers. And so yeah. And next up are the rational numbers. And so for the integers, sometimes we represent it with this kind of a z, which is considered a special symbol. Oh, right. Let me turn this into. Oh no. Okay, I'll turn into red. Okay. So yeah, and so for the rational numbers, the symbol is this special Q. So what a rational number is, so one possible definition is simply just m over n for m and in z. And so when I say m, n, and z, what this means is that m and n are integers. So yeah. So the rational numbers are all numbers that can be expressed in the form m divided by n for integers m and n. And so next up are the real numbers. And what the real numbers are basically just about, just quite literally any of the numbers that do not involve complex numbers. So what I mean by this is a bit harder to explain, but basically what I mean by the real numbers is the rational numbers plus the set of irrational numbers. And so the set of irrational numbers is a lot harder to explain. So I'll just give a couple examples of real numbers to show you. So once again, the real numbers include the integers. Yes, just like the rational numbers. So some examples we 1, 0, -1/2, 1, 100 over 11, and so on. And so just like that, the real numbers, so some possibilities would be 0, and the rational numbers are also part of the real number. So a real number could also be something like 11 over 21. And yeah. And so now those are integers and rational numbers for now. So now let's move on to numbers that are not integers or rational numbers, but are still real numbers. So one example will be the square root of 2. And if you don't know what square root of 2 means, it just basically means the number, if the number that you square to get to. And if you want to know what it is, it's approximately 1.414, something. And it continues infinitely on, and the pattern isn't repeatable, so yeah. So another way you could define the rational numbers would be by using decimals. So if you use decimals and the pattern repeats at any point, then it'd be rational. For example, 1.5141414 and 14 repeats infinitely on would be considered rational. But if it's something like 3.141592, okay, 93, I guess 6535, 89, so on, and where there is no pattern at all, then it would be considered irrational and would not be a rational number, but only be counted in the real numbers. So if you couldn't tell, 2, okay, this should be 2. And if you couldn't tell, the number here I was writing are the first couple of digits of pi. And another famous irrational number would be e. And so pi and e are slightly unlike that of square root 2, and it's because pi and e have a property where they are called transcendental. And what transcendental means is that they are not they cannot be roots of any polynomial with integer coefficients. So for example, root 2 can still be a root of x squared minus 2. And this is a polynomial with integer coefficients. But pi and e cannot. And so other examples of real roots, real numbers, will be like the fourth root of 5, or the cube root of 6 plus the seventh root of 8, and so on. Okay. And so next up are the complex numbers. And so the complex numbers are represented with this special C. So what the complex numbers are, they're basically the complex numbers are m plus n times I for m and n in C. Oh, not C, sorry. For m and n in R. And also where I is the square root of -1. And so, yeah. And if you couldn't tell, it's called complex numbers. And this cannot be simplified purely because we don't really have a number exactly for the square root of -1. So we just call it I. So yeah. And actually the complex numbers are quite useful, as it turns out later on. So some examples. So just because m and n just because the number is called complex does not mean it necessarily cannot be a real number. So for example, 0, 1/2, and e are still complex numbers, but now there are also numbers like 1 plus root 2i. Oh, and root 2 is another way of saying the square root of 2, and it's basically an abbreviation. And so another would be like e plus pi I, and so on. And so something we should note, okay, is that all of these sets will satisfy are closed on the standard operations of multiplication and addition, where the times and the plus symbols mean exactly what they mean in just our normal math. And so all of the numbers also have additive and multiplicative inverses. And so what that means is basically the additive inverse of a number is simply just oh dear. Okay, this might be a problem. Okay, there we go. Alright. So basically, an additive inverse, the additive inverse of x would just be -x. And as you can probably guess by the additive inverse, it's called the additive inverse just because technically the definition of an additive inverse is the number a such that x plus a is the identity in addition, which would be 0. And what I mean by identity is basically the number. So if I represent the identity by e and the addition by the plus, then it's basically what we can substitute into e such that this equation is true for all x. And so obviously the identity would be 0. So we can plug that in here. So it means that the additive inverse of x is negative x. And similarly, the multiplicative identity is when x times e is equal to x. So e is 1. So the multiplicative inverse is the number a, such that x times a is the identity, which is 1. And so the inverse, the multiplicative inverse of x is 1 divided by x. And so another thing we know is that the numbers satisfy the operations satisfy the commutative and associative properties, and combined they also satisfy the distributive property. So the commutative property is basically for any operation which we can just call star. The commutative property is that a star b is equal to b star. Oh, that's not a star. Okay, b star a. And similarly, the associative property is that a star of b star of star c is equal to a star b of star c. Okay, excuse me for a second. Okay, sorry about that. And so obviously the distributive property is just the one that we know, which is a times b plus c is equal to a times b plus a times c. Yeah. Okay. So yeah, so that's basically the foundations of the numbers. Okay, yeah. So those are the foundations of the numbers. So yeah, and you can see the special notation that normally gets used here. So next is a slight introduction to modular arithmetic. So basically, it's written as a mod m. So a number is written as a mod m, and so normally we work in modular arithmetic with the given assumption that a and m are integers. And so then a mod m is some number of the sets, is some member of the set of numbers from 0 to n minus 1. And this symbol here is used to mean congruent. So some of the basic rules of modular arithmetic. So this first rule is more of a definition than a rule. So if A is congruent to B mod M, then A minus B is equal to K times N, M for some K and Z. So basically, another way we can think of modular arithmetic Okay, sorry about that. So I'll just go back a bit. I'm not sure exactly where I got to, so I'll just go back a bit. So basically, A is congruent. A mod M is basically congruent to the remainder when A is divided by M. And so now one of the most important, it's basic, but it's really quite important. It's a basic rule, but it's really quite important. So if A is congruent to B mod M and C is congruent to D mod M, then you can see that A plus C is congruent to B plus D mod M. And we also have that A times C is equal to B times D mod M. So basically, some simple examples of this would be something like, oh, sorry. Oh. Okay, there we go. Okay, that's not much better. Okay, there we go. So basically, some simple examples would be like 5 is congruent to 2 mod 3, and negative 10 is congruent to let's see, 2 mod 4, and it's also congruent to 42. Yeah, stuff like this. So that's the basic definition of modular arithmetic. And so next is GCD and LCM. So the GCD stands for the greatest common divisor. And basically, GCD of a certain group of n numbers where n is at least 2, or basically n is greater than 1, is the largest number that divides all of the n numbers involved. So when I wrote it down, I basically use A1 to A1, A2 to AN for integers n and n greater than 1. But basically what I'm saying here is the GCD of a certain group of numbers with more than one number is the largest number that divides all of the n numbers. So a simple example of this would be GCD of, for example, 6 and 9 is equal to 3, and GCD of 1 and 15 is equal to 1. Yeah, and so next is LCM. And so it stands for least common multiple. All right, and another thing you to note is that sometimes the greatest common divisor also gets abbreviated to GCF. And in the GCF, it's the exact same thing. It's just that the word that gets abbreviated is different. It goes from greatest common divisor to greatest common factor, but more commonly the thing that is used is GCF rather than GCF. So, but as far as I'm concerned, there are no other alternates ways of writing LCM of stuff, unless you want to include the brackets, but those are confusing. So the LCM, basically, I use the same notation as the one from earlier. This notation is the exact same. So once again, what it means is that this LCM is basically the smallest number that is the multiple of all of the n numbers involved in the parentheses here. And so some examples of this, okay. Once again, please wait a while. Sorry. Okay, there we go. So once again, LCM is least common multiple. And so some examples would be LCM of 6 and 9 would be 18. And the GCD of 1 and 15, oh sorry, not GCD. LCM of 1 and 15 would just be 15. And you might notice something interesting if you look at how the GCD and LCM pair up. And so, yeah, you might notice something interesting if you do that. I won't go over in too much detail now, but if you manage to find a pattern, I'll just tell you that what you found is probably correct. And yeah. So next up is the Euclidean algorithm. So for example, so what it means is...
No, Euclidean geometry is not an algorithm.
Please wait for a second. Okay, sorry, I don't know how that happened. So Euclidean algorithm. So basically what it says is that, so it's basically a repeated process based off of the idea that the GCD of A and B is the GCD of A minus B and B. And this can be repeated indefinitely until the GCD is found. And so in a similar manner, in fact, this is more commonly used in the Euclidean algorithm than this. And it's just because of the simple fact that this makes it a lot shorter than this. Oh yes, and something to note is that K is obviously still in C. So I'll show you some examples of the Euclidean algorithm in here. So the first one should be fairly obvious right off the bat. GCD of 15 and 73. So basically 15 times 4 is equal to 60. So 73 minus 60 is 13. So yeah, so GCD of 13 and 15. And so next, this is equal to just straight up GCD of 2 and 13. And by this point, even if you didn't see it by the start, you should be able to tell by now that this is 1, but I'll still continue. So 2 times 6 is 12, and 13 minus 12 is 1. So it's GCD of 1 and 2. And by this point, it's just clear that it's 1. There's nothing else you can really do. And so next is an example of a GCD where the GCD is not 1. So we could use GCD of 20 and 55. So 20 times 2 is 40, and 55 minus 40 is 15. So this is GCD of 15 and 20. And so if you subtract 15 from 20, you get that it's GCD of 5 and 15. And if you subtract 5 from 15 3 times, this is GCD of 0 and 5, which is clearly just 5. And so the final example I'll be doing is just an example where it's really not obvious.
I don't know that.
Sorry. So it's an example where it's really not obvious what the end result is going to be. So GCD of 1001 and GCD of 1440. Okay. So yeah. So this is equal to the GCD of 1449 minus 1001 is 448 and 1001. And this is equal to GCD of 448 minus 2 is times 2 is equal to just 896. And so 1001 minus 896 is just exactly equal to 105. So this is GCD of 105 and 440. And if we multiply this by 4, we get that this is 420. So if we subtract that from 448, this is GCD of 28 and 105. And so once again, if we multiply 28 by 3 and subtract it from 105, the end result is that you get 21. So this is GCD of 21 and 28. And so 28 minus 21 is 7, so GCD of 7 and 21. And by this point, we can all see that it's just 7. Okay. So yeah, so back to this. So finally, so the Euclidean algorithm is quite important. And so finally is another rather important thing to know. It's called lemma, but it's really well known. So I guess you can consider it a theorem by now. So basically, we abbreviate GCD of x and y to just d, then the minimum positive value of a number that can be expressed in the form ax plus by for integers a and b is d. So what I mean by this is basically any combination of this form would always be be at least d. So some examples would be with just small numbers here, 3 and 7. So 7 minus 2 times 3 is 1, and obviously there's no other way we can decrease. Oh, and another thing we can easily see is that obviously any number of the form ax plus by is divisible by the GCD of x and y, which is d, and that's just purely by the definition of GCD, because it divides both x and y. So it's impossible for the number to not be divisible by d itself. So if basically, as long as d is achievable, then the minimum positive value would always be d. So another example here would just be that 10 and, for example, 24. So 24 times 3 minus 7 times 10 is 2. Because 24 times 3 is 72, and 7 times 10 is 70, and 72 minus 70 is 2. And well, okay, yeah. I guess that's basically all I really wanted to cover in my lecture on number theory. So that's and so next is I think Catherine, and she's going to go over the weekly programming challenge questions.